Good evening to all. Today we are going to discuss about thermodynamic process for constant temperature, and this is also called isothermal process. So I'm sure this video is going to be very interesting. So please subscribe the channel and don't forget to hit the bell icon. Thank you. So let's begin the discussion for isothermal process for ideal gas. Thermodynamic system is if you say what is thermodynamic system, it is the gas which is called the thermodynamic system, and gas can be air or gas can be any hydrocarbon. So it is not compressor, it is not turbine, but it is the gas which is called the thermodynamic system. So our focal point is only the gas. So if you see, there is some uh, sign convention for the first law of thermodynamics. So if heat is added to the system, means heat is added to the gas, it is considered positive, and when heat is taken from the gas, it is considered negative. Similarly, when work is done by the gas or by the system, it is positive, and when work is done on the gas or by on the system, it is negative. When the energy level of the thermodynamic system increases, it is considered positive. When decreases, it is considered negative. This is the sign convention. Ideal gas of equation of state PV is equal to N RUT. On simplification, we can write P small v RT, where P is a pressure, V is the volume, small v is the specific volume, T is the temperature, small m is a mass, capital M is in mole weight, RU is universal gas constant, R is a gas constant, and N is number of moles. So this is the most important formula that is used. Now the types of thermodynamic system: open system when there is a flow of mass in and out, and as well as energy transfer is called open system. In closed system, there is no flow of the mass but only energy transfer. In case of isolated system, neither mass transfer occurs nor the energy transfers. Work transfer on PV diagram. Work transfer is mentioned for the closed system. It is a under integration of PdV, so which is equal to area under the curve on x-axis. On open system minus VdP, and area on under the curve on y-axis is called the work. For open system, work by the system is positive, work on the system is negative, and work transfer per unit mass is called the work head. Energy transfer. Energy transfer for the closed system is internal energy change. So energy transfer for the closed system is integration of CV dt. Energy transfer for the open system is equal to enthalpy change. So energy transfer for the open system is integration of Cp dt. So energy of the system, if increases, it is positive. When energy of system decreases, it's called the negative, or it is considered negative. As per the first law of thermodynamics, the efficiency of the thermodynamic machine is considered 100% efficient. That means there is no losses of during the heat transfer, work transfer, or energy transfer. So heat transfer is equal to work transfer plus energy transfer. This is first law of thermodynamics. So Q is equal to W plus E. Now the process, thermodynamic process, that is isothermal process or constant temperature process for ideal gas. This process is isothermal, that is temperature remains constant. You can see in the PV diagram, 1 and 2 is a compression process where pressure increases, volume decreases. Similarly, 1 and 2 is again reverse expansion process, volume increases, pressure decreases. On TS diagram, you can see 1 and 2 as temperature remain constant but entropy increases. 1 and 2 again compression process. Sorry, this one. So on TS diagram, you can see in both the temperature remain constant because this is isothermal process, and on PV diagram you can see the compression process, expansion process. But the here case is the reverse. In PV diagram, when the volume, this decreases, pressure increases. When volume increases, pressure decreases because temperature is constant. Now the isothermal process in the closed system. So work transfer per unit mass can be derived as temperature is constant. So T is equal to T1 plus T2. Sorry, T is equal to T1 is equal to T2. T is remain constant. Ideal gas PV is equal to RT. P1 V1 is equal to RT1 and PV P2 V2 is RT2. But T1 T2 are same. So we can write P1 upon P2 is equal to V2 by V1. Again, the ideal gas relationship Cp minus Cv is equal to R, K is equal to Cp by Cv. So for the closed system, we can write W is equal to integration of PdV, and P can be replaced as RT by V. So we can write after integration RT1 is equal to Ln means log, natural log, V2 by V1, and which is replaced as W is equal to RT1 into P1 by P2. So work transfer per unit mass W is equal to RT1 Ln P1 by P2, and total work transfer mass into RT1 into Ln P1 by P2. So on PV diagram, we can see area under the curve on x-axis is called work or or work transfer. So you can see here. Now energy transfer, since then there is no change of temperature, so energy transfer is zero. Heat transfer, you can see as per first law of thermodynamics, Q is equal to W plus E is zero, so Q is equal to W, which is equal to RT1 log P1 by P2. So heat transfer per unit mass Q is equal to RT1 log P1 upon P2, and total heat transfer is equal to M into RT1 log P1 by P2. On TS diagram, you can see the area under the curve on x-axis called the heat transfer. So when heat is increasing, the entropy increasing. When heat is decreasing, entropy is decreasing. Entropy change, S is equal to Q by T. So we can write Q, but Q can be written as integration of RT by V, integration of RT by V into dV. So S is equal to integration of RT by V divided by T. So you can write integration of R by V into dV. So we can further write S is equal to R into ln V2 by V1. Ln is a natural log. So we can write S is equal to R into ln V1 P1 by P2, because this is replaced. V2 by V1 is P1 by 2. So entropy change per unit mass S is equal to R ln P1 by P2. Total entropy change mass into R ln P1 by P2. So this is entropy change on TS diagram. Now the same all this work transfer, heat transfer, and energy transfer for the open system. So now the on PV diagram, area on the y-axis will be the work transfer. So we can see this same equation. Process T is constant, T is T1 by T is equal to T1 is equal to T2. Ideal gas equation PV is RT P1 V1 RT1 P2 V2 RT2. Ideal gas relationship Cp minus Cv is equal to R, K is equal to Cp by C2. So work transfer W is equal to minus integration of VdP. So we can further write minus V RT upon P into dP, because V is replaced with this RT by P, and so we can write V is equal to W is equal to minus RT1 into log P2 by P1. Ln is log, natural log. So further we can write W is equal to RT1 in log P1 by P2. This is replaced, sorry, minus coming this, it is changed. It is now P1 by P2. So work transfer per unit mass W is equal to RT1 ln, that is natural log P1 by P2. Total work transfer mass into RT1 ln P1 by P2. Energy transfer will be zero because there is no change of temperature. So heat transfer will be the work transfer, which can write RT1 ln P1 by P2 per unit mass. Per total mass, you have to multiply with the mass. So this is also shown area under the curve on TS diagram is the heat transfer. Now the entropy change, S is equal to Q by T. S can be written as minus integration of RT by P is dP is Q, which is equal to W, and S will be divided by T. So T is cancelled out. We can write R by P into dP integration. So we can write S is equal to R minus R into ln P2 by P1, which is equal to R ln P1 by P2. So this is entropy change. R ln P1 by P2, total entropy change will be M into R ln P1 by P2. So this is for entropy change for the open system. Now let us understand the with an example. So nitrogen gas has initial pressure and temperature are 0.5 bar gauge, 30 degrees Celsius respectively. Gas is compressed such that the final pressure reaches to 0.8 bar gauge constant on constant temperature with consideration of ideal gas. Calculate work, heat, energy transfer and entropy change during this process for considering closed system and open system. Also calculate inlet and outlet specific volume. Following data are given: mole weight of nitrogen 28 kg per kilomole, universal gas constant 8314.5 joule per kilomole per Kelvin, specific heat capacity at constant volume 20.86 kilojoule per kilomole per Kelvin, local barometric pressure 1 bar absolute. Now these are the data given. For the closed system, we are taking barometric pressure is 1 bar, absolute temperature 273.15. Inlet pressure is gauge pressure plus barometric pressures. It is 1.5. Temperature is 30 degree. Outlet pressure in absolute is 1.8. Molecular weight CV is given. R is given. Now we can further gas constant dividing by R. It is this. CV is converting joule per kg per Kelvin by dividing R M and multiplying 1000. It is 745, and Cp is equal to Cv plus R, which is this, and then K is Cp by C, this is this, and then inlet specific volume is calculated like this, and V2 is also calculated this. Work transfer for the closed system is minus 16412. Internal energy is 0, so Q is equal to minus 16412. Entropy change is minus 54. Now for the isothermal process in open system, only change is work transfer, which is 16412. Internal energy transfer is 0, so heat transfer will be same, that is 412. Entropy change is minus 54. This is for the open system. So I hope you have enjoyed this. Thank you for watching.